This video is supported by CuriosityStream. Like many of you, over the last few months I've been sheltering in place as much as possible, and to pass the time I've been watching a lot of documentaries, and for some reason I keep going back to documentaries about the Black Plague, because they're just such a pick-me-up, you know? I don't know, I'm just kind of fascinated by how humans have dealt with situations like this in the past, and the Black Death just seems like the ultimate example of this. And I'm also fascinated by how, situations like this have changed the world going forward afterwards. But one thing that I keep thinking about in terms of the Black Death is that, as bad as everything is now, at least we know what viruses are. At least we understand germ theory and we know at least what we're dealing with. But back then, they had no idea. They had no concept of germ theory whatsoever. I mean, just imagine how terrifying that must have been when just everybody's just dropping dead around you and you have no idea why. I mean, I seriously wonder what would happen if you went back in time to the Black Death and tried to explain to them that actually it's these tiny little bugs that are too small for your eye to see, and they get into your bloodstream and they tear apart your cells and... Oh, what are cells? Right. Well, I feel like one of the great through lines of science over the years has been the constant breaking down of things into smaller and smaller components. Cells, organelles, molecules, atoms, protons, quarks. It just goes on and on. Whenever we think we've found the smallest thing, there's always something smaller. So imagining that at the smallest scales, what you basically get is this, sounds insane, but not any crazier than trying to go back to the 13th century and explain to them what viruses are. And yet there's an entire field of science that revolves around this idea. It's the fabled string theory, and just like everything else, just when you think you've gotten to the bottom of the rabbit hole, there's more rabbit hole. Who here remembers life before smartphones? Or before any kind of cell phone was common? Who here remembers before there were any exoplanets? Anyone? Bueller? Anybody here get the Ferris Bueller reference? The point is, all of that stuff I just listed happened incredibly recently. In the time that I've been on Earth, there have been some major sea changes in science. And that happens from time to time. And that happened in physics at the beginning of the 20th century. In 1905, a young patent clerk named Albert Einstein had what they called his miracle year. He published a series of papers that completely revolutionized our understanding of light and gravity and the universe itself. And it earned him an invitation to the first Solvay International Conference on Radiation and the Quanta in 1911. As you can probably guess from the name, the conference was all about quantum mechanics, which had just kind of been theorized, and there were still a whole bunch of different competing theories out there. It was kind of the Wild West of quantum mechanics at the time. Einstein's photoelectric theory, which explained how photons can eject electrons from material, was quantum in nature, so he was invited to speak on that. But not everybody was on board with it yet, and he wasn't really that big of a deal at the time. I mean, yeah, he had some cool papers that had been published, but 6 months before that, he was a patent clerk. By 1927, when the fifth Solvay conference was held, Einstein was a megastar. A lot had changed since then. Quantum mechanics had basically been stripped down to its core and rebuilt. A lot of it based around Einstein's theories, and he came into that one like a boss. Even so, this particular conference kind of became famous because of a bit of a squabble between him and Niels Bohr over the nature of quantum mechanics. Bohr's Copenhagen interpretation hinged on the idea that quantum objects, quantum particles, were inherently random in nature. But Einstein liked the idea of a deterministic universe, and he didn't like that, so he said, no dice. Actually, what he said prompted one of my favorite physics exchanges of all time. He told Bohr, God does not play dice with the universe. To which Bohr replied, Einstein, stop telling God what to do. Oh, physicist drums! Unfortunately for Einstein, his deterministic view of the quantum world started to lose popularity over time, especially after Enrico Fermi discovered the weak force in 1933. Before that, there was just electromagnetism and gravity, and at that point, Einstein's ideas made sense. But the discovery of the weak nuclear force and later the strong nuclear force kind of upended everything, and then Einstein's theory of gravity on the quantum scale just didn't make sense anymore. Now flash forward to the 80s, and electromagnetism and the weak force were found to be expressions of a single electroweak force that would come together at extremely high temperatures. And the strong force can be explained the same way, theoretically, the idea being that in the early hot universe, there was one singular unified force that was acting on all particles all the time, and then it eventually diversified into the forces that we see today. Imagine a snowflake. As the water cools, it forms symmetrical bonds that give the snowflake its shape. melt the snowflake and refreeze it, and the bonds might form in a different way. Similarly, that single unified force froze long ago into electromagnetism and the strong and the weak force. But gravity is the holdout. Gravity is that guy you know that just has to be different. For example, the electromagnetic weak and strong forces all work through force carriers called photons, bosons, and gluons, respectively. And Einstein was fine with this, at least when it came to electromagnetism, but he drew the line at gravity. Because to Einstein, gravity wasn't a force, it was kind of a quirk of geometry. That was sort of the whole idea behind general relativity, was that mass curves space-time itself. So objects curve through a gravity well, but they're actually following a straight line. There's just no neat way to fold gravity into a grand unified theory of forces. It's just far too weak to have ever played on the same football team as the other forces. You know, unless there's some deep structure or quality of matter that explains the differences, gravity just kind of has to be its own thing. Physicists are like preschool teachers, you know, they're just trying to keep order in the classroom, and all the other forces are over here drawing, minding their own business, and then there's gravity sticking gum in someone's hair. Gravity, why can't you be normal? So out of all this, some scientists and mathematicians began working on a deep structure kind of theory to explain all of this. And their work eventually became string theory. So before I dig into string theory, let me just back up a little bit. Somehow, in 5 years of doing this channel, I've never actually covered string theory. Considering all the topics I do on here, that seems impossible, and yet it's true. And I'm wondering if I put it off because subconsciously I don't feel like I fully understand it myself. You know? I mean, don't get me wrong, I've covered all kinds of theories that I don't fully understand, but those are usually kind of fringy theories that haven't been really fully explored, whereas string theory has been very explored in a lot of places, and it's very mathematical, which I am very not. So I guess I always kept it at arm's length. Wouldn't be the first time I've pushed someone away just because I didn't understand them. All right, so the thing about string theory is that you have to think sort of extra dimensionally, which is kind of impossible for the human brain to do. We all, of course, know Sagan's Flatland analogy, which he actually took from Edwin Abbott, the idea that if you had two-dimensional creatures living in a completely two-dimensional world with no up or down, no third dimension, it would be almost impossible to get them to conceptualize what that third dimension might be like. Similarly, with string theory, we have to think of a fourth dimension and higher dimensions, and it's just kind of impossible for us to imagine. But the thing is, the math works. So we start with 4 dimensions that we know, 3 spatial dimensions and 1 time dimension. And the first effort to apply another dimension onto that, a 5th dimension, is Kaluza-Klein theory. Theodore Kaluza was a mathematician who devised this original idea around 1919. He was trying to find a way to unify gravity and electromagnetism by basically making both of them a quirk of geometry. So he applied a 4th spatial dimension to Einstein's field equations, and what he found was that when doing that, electromagnetism emerged alongside gravity. More on that in a minute. A student of his named Oscar Klein would later refine it a little bit by saying that electromagnetism was the result of motion through the 5th dimension. I've heard this explained like, imagine you're an ant walking on a power line. And yes, there are the regular 3 dimensions that we're all aware of, but you can also go around the wire. There's sort of a looping dimension there. And similarly, Kaluza imagined his 5th dimension as a cylinder. Klein would later imagine it as an extremely small closed loop, and it's that compactification that makes it invisible. Klein proposed a 5th dimension so small that nothing in the macro world could experience it directly. You know, quantum objects might loop around and fly through it, but anything as big as us would never directly observe it. And Einstein was actually a fan of Kaluza-Klein theory, but he did feel that it was incomplete. In fact, Kaluza shared that opinion with him, saying that it had physical and theoretical difficulties in his original paper. One of the major objections was that there wasn't really a reason for the extra dimension to be so small, and it also didn't account for all the subatomic particles that we suddenly began finding. As we started to understand the role of force carrier particles, the 5th dimensional idea just sort of hit a dead end. You know, particle physics moved on, and 5th dimensional physics kind of became a footnote in science history. So in the 60s and 70s, a whole bunch of particle accelerators came online, and we started to find proof of theoretical particles that we'd never seen before, and this led to what's known as quantum chromodynamics. Quantum chromodynamics are all about the quarks and the different varieties of quarks that make up the protons and the neutrons, the red, the blue, the green, the up and the down quarks, and so on. Now this solved a lot of the issues around the strong force, and it started to look like our full understanding of the quantum universe was going to be just right around the corner. I thought they had it. That's adorable. The thing was, in the middle of these particle collisions, they started to notice some vibrations, especially in some particle-antiparticle pairs that were happening that seemed to resemble vibrating strings. This was hard to explain. Unless they were interacting with some weird geometry from another dimension. So the extra-dimensional idea started getting dusted off a little bit, and several different versions of it started going around postulating that the universe was made up of vibrating strings, tiny vibrating strings that vibrate in 4 spatial dimensions and 1 time dimension. By the 80s, string theory was the new hotness, partially led by Edward Witten of the Institute of Advanced Study at Princeton. Quantum chromodynamics was cool and all, but it still didn't explain gravity. So a lot of these physicists just got tired of trying to make gravity fit into a 4-dimensional universe and were like, look, if that crazy higher dimensional math stuff works, I mean, Mathematically anyway, string theory was starting to look like the grand unified theory we'd all been waiting for, going all the way back and explaining all the mysteries all the way to the Big Bang. This is what Einstein wanted. Except for determinism. Einstein's beef with randomness doesn't get solved by string theory. It does allow for particles to have random values in their states. Now there is room for both randomness and determinism if you try hard enough. There is sort of a side theory in string theory that proposes that there's 10 to the 500 universes making up a giant multiverse. And each of these universes would have different physical laws, so some of them may be deterministic and some of them may be random. Is that cheating? Feels like cheating. But that's a whole other rabbit hole. Let's get back to string theory. So yeah, according to string theorists, the universe is made up of tiny vibrating strings. Very tiny, possibly the most tiniest possible thing that could possibly exist in the possible universe. Yeah, an actual measurement in meters would be something like a decimal point followed by 34 zeros and then a 1. At that scale, a string would be able to move through multiple invisible dimensions. So Kaluza-Klein recommended there was only 1 extra dimension, others had different numbers. 10 and 26 were popular numbers for mathematical reasons. But yeah, once the foundation for string theory was laid down, it quickly devolved into many other different types of theories, including superstring theory. Yeah, superstring theory accounts for all of the known particles in the standard model of particle physics. That means the fermions that carry matter and the bosons that carry forces. So yeah, fermions and bosons are considered to be supersymmetrical in superstring theory, so every fermion would have a boson partner and vice versa. The bad news is this means there are a lot of theoretical particles that have not been discovered in the standard model. The good news is this means it's actually testable. If you can find those particles, then you got some pretty good evidence for superstring theory. But yeah, string theory in general has been criticized for being untestable, but in superstring theory, again, you find those bosons, you're good. And as superstring theory evolved, the number of dimensions kind of got whittled down. I said earlier that 10 and 26 were popular numbers. Eventually 10 started to win out. So of course, just as the dust began to settle on that debate, Ed Witten and his team shook things up again in 1994 with a second superstring revolution. This time they added 1 more dimension for 11 dimensions total, and they called this one M theory. The extra dimensions were compactified and folded in on top of each other to create what they call a calabi-yau manifold, which sounds like a part on a spaceship in a sci-fi movie that keeps breaking. We're not going anywhere, Captain, not without a new calabi-yau manifold. But yeah, remember that power line analogy that I used earlier with the ant? Well, so it has that 1 dimension of looping, so you can imagine if you cut that open and there were like a bundle of wires inside of it, all of which loop in and around, and the ant could go down and around it. That's one way of making sense of it. At least it's the best I can do without having a stroke. So in standard quantum physics, particles are assumed to not have any dimensions at all. They're expected to be point-like. But in M theory, the strings might be 1-dimensional, or they might be like a membrane, all scrunched up and wrapped around inside multiple invisible other dimensions. Technically, a membrane has only 2 dimensions, so any similar construct that has multiple dimensions is known as a brane. So now we are getting into brane theory. And you can combine these invisible membranes into groupings and then give a prefix with the number of the groupings, like say 5 brane, or in my case, melted brane. I mean, this is where I'm like, what? For fans of The Good Place right now, I'm Cheaty trying to figure out the dot over the I and the Jeremy Bearimy.
This broke me. The dot over the I. That broke me. I'm done.
But the math works. There is math that shows that one-dimensional strings and membranes, five branes, can all account for all the forces and particles that we see in our physical reality. There is math that shows that vibrating strings can create the mass, the charge, the spin of all the particles of the standard model, as well as all the predicted particles from supersymmetry. The math makes all this work, somehow. But is that because we discovered some fundamental truth about reality? Or is that because we were so desperate to make the math work that we created several invisible dimensions just to make the math work? I don't know, I'm asking. But what about gravity, though? That was the problem child that got us here in the first place. How does brain theory and M theory account for that? Well, each force has a carrier boson in M theory. We have the 3 of the 4 bosons accounted for, so according to M theory, there should be a gravity boson. Now you might be asking what happened to Einstein's theory that gravity is just a quirk of the curvature of spacetime. Well, when Kaluza and Klein added another dimension, that kind of changed the rules a bit. See, I remember what I said earlier about electromagnetism sort of emerging alongside gravity when you add a fourth spatial dimension. What I meant by that is that movement through that 5th dimension, in math anyway, creates an electromagnetic force. Electromagnetism has the photon as its boson, so with gravity, it would have the graviton. All right, kids, so today we learned string theory postulates that the fundamental units of our universe are vibrating strings. Fermions and bosons are the 4th dimensional result of those vibrations. Superstring theories are string theories that include a partner boson for each fermion. M theory is a modern superstring theory. It says spacetime has 11 total dimensions, 10 of space and 1 of time. And the strings in M theory may be one-dimensional, like a line on paper, or they may be branes with multiple dimensions that look like strings when more dimensions are considered. All fundamental forces, including gravity, are mediated by bosons and superstring theories, including M theory. If you stare too long at the abyss stares back at you. That was said by Batman, I think? He may have been quoting somebody else. I don't care. The mental gymnastics required to imagine a calabi-yau manifold are it's a lot. And this is, of course, a video that just scratches the surface of string theory. There's way, way deeper and mind-meltier that you can go. String theory is kind of an umbrella concept at this point. Like I said, there's an entire field of study around it, so it's hard to just kind of dismiss it at this point. But is this actually leading anywhere, or is it just magic math? Well, I mentioned a couple of testable conclusions from string theory, that there would be some undiscovered bosons out there that people have been looking for in particle accelerators ever since then. And that was actually one of the many high hopes for the Large Hadron Collider when it went online, that it would find some of these bosons. It didn't. At least, not so far anyway. But yeah, these particles exist on a range of heaviness where they're expected to be found, and the experiments at LHC have actually pushed up the level of heaviness that these things would have to be. Turns out they're kind of chunky. In fact, some of these particles are heavier than some other particles that we found at the LHC, including the Higgs boson, so it's starting to feel like if these particles exist, we probably would have found them by now, which means that the most testable prediction about string theory so far hasn't really yielded any results. And another problem when it comes to the testing of string theory is that whole 10 to the 500th universes in a multiverse thing, because anything that doesn't actually get found here in this universe, a physicist could just say, well, that's because it exists in another universe. I mean, imagine trying to pick the one marble out of a jar filled with 10 to the 500th number of marbles. And as for all those invisible curled up dimensions, there's no experiment that's come anywhere near proving that. Now, there was an experiment conducted recently using the Chandra X-ray telescope that had some promise for string theorists. The results of that actually were just announced in March. So yeah, Chandra was looking for axions, which are particles that are predicted in superstring theory, and they were looking for it around a black hole in the Perseus cluster. The idea is that axions would convert to photons in a high and strong enough electromagnetic field, so it was looking at a black hole looking for some of those axion-photon conversions. And another swing and a miss. Now, it is possible that the conversion level that these axions go through was actually just out of the range of what Chandra was looking for, but it's also just as possible that they're just not there. Now, this doesn't rule out string theory, but it is yet another setback in a long string of setbacks. Oh, come on. So, that is everything I know, or think I know, about string theory. Please feel free to correct anything I got wrong down in the comments, like I need to ask. Like I said at the beginning, there's a ton of great content out there on string theory by people who know 1,000 times more about it than I do. I will link to some of that down in the description for you. And it really is more of a math theory. Like if you were to ask me if I think it's real, all I could say is I can't say that there's been any real evidence out there of it outside of the math, which is so complex that I would never understand it even in a million years. But that doesn't mean much. I mean, the same could be said for the algorithms and the engineering and the math behind the pixels that you're looking at on your screen right now. And yet, there they are. So, yeah. So I will reserve judgment and just keep trying to understand it a little bit better. And I hope, if nothing else, this video served as a jumping off point for you to do the same thing. Thanks for watching. But yeah, quantum physics just kind of messed up everything. You know, we had a pretty good handle on the world, and then it just... Yeah, the whole reason string theory even exists is to try to make up for all the weirdness of the quantum world. So if you want to understand all that a little bit better and see how we got to where we are right now, I can highly recommend Secrets of Quantum Physics on CuriosityStream. Hosted by Jim Al-Khalili, this series tells a story of quantum physics, of how we learned what we know, the surprises we found along the way, and how it's changed our understanding of the universe. This is, of course, just one of hundreds of documentaries on CuriosityStream on everything from science and history to technology to nature. CuriosityStream is the streaming service for high-quality documentary content. I legit watch this streaming service more than any others right now, I'm not even joking. And now, when you sign up for CuriosityStream, you also get a free subscription to Nebula, the streaming service featuring ad-free content from some of your favorite educational YouTubers like Real Engineering, Real Life Lore, Polyphonic, Tom Scott, and if I dare include myself in this group, I'm on there as well. There are also Nebula originals that you can't find anywhere else. Anyway, that's totally for free when you sign up for CuriosityStream, and you can get CuriosityStream totally for free for 30 days anyway when you sign up at curiositystream.com/Joe Scott, and after that, they're actually offering 40% off their subscription service for quarantine reasons, and it was only $2.99 a month to begin with, so 40% off of, I mean, you will never pay so little for so much in your entire life. Anyway, I love CuriosityStream, can't recommend it enough. Link is down in the description, curiositystream.com/Joe Scott, go check it out. Big thanks to CuriosityStream for supporting this video, and a huge shout out to the Answer Files on Patreon that are helping me build a team, forming an awesome community. We got some new people who have joined. Let me murder their names real quick. We've got Howa Vang, James N. Weiss, William Droll, Jacob Fresca, Matt Dizak, Gone 9 Clarity, Primo Catalino, Gabe Frail, Steve Kyle, David Wilsey, Carrie Brown, Jasmine Gunning, Braditude, love it, Rick Kenny, Chuck Floyd, Jonathan Schultz, Didi Spontak, Shannon Giro, and Sarah Britton. Big supporter. Thank you guys so much. If you would like to join them, get early access to videos and some exclusive content you can't find anywhere else, including live streams, you can go to patreon.com/answerswithjoe. T-shirts available at the store, answerswithjoe.com/store. There's also hoodies, mugs, stickers, posters. They're fun, they're nerdy, they make a statement, people will think you're cool, and there's channel branded stuff there if you want it. Anyway, it's there, go check it out. It helps support the channel, answerswithjoe.com/store. Please do like and share this video if you liked it, and if this is your first time here, maybe check out this one, because Google thinks that you might like that, or any of the others on the side with my face on them, and if you enjoy those, I invite you to subscribe. I come back with videos every Monday. All right, thanks again for watching. You guys go out there now, have an eye-opening week, stay safe, and I'll see you next Monday. Love you guys. Take care.